Alright kids, today we've got a block which is connected by a string that runs over a pulley to a hanging mass. Now this block is sitting on a level surface which is rough, meaning there's some friction between the block and the surface. And we're going to solve for the minimum value of this hanging mass that's going to cause this block to move. Now this problem is all about force, so the first thing we're going to do is draw a free body diagram for each of these blocks. So looking first at the block on the table, first there's the force by gravity on the block. And then there's the normal force, which is really just the table holding up the block. Now since this hanging block over here is in fact hanging, there's going to be some pull force in the string, which we're going to refer to as tension. And last there's friction, which is acting to the left on the block, keeping it from going anywhere. Now looking at the hanging mass, there's gravity which is trying to pull it down, and the tension in the string which is holding that mass up. So now that we've laid out all the forces acting on each of these objects, we can take a look at Newton's second law in order to figure out exactly what's happening mathematically in this problem. Now Newton's second law says that the sum of all forces on any object is equal to that object's mass times acceleration. But the catch is, in this problem, we're looking right at that critical transition where the mass isn't quite accelerating. So what we're going to do in this problem is we're going to let acceleration equal 0. And we're going to apply that concept along with the second law to each of these objects. So starting with this block up here, I want to apply the second law in the plane of motion of the block. Or really, I just want to look at the forces which are acting in the direction that the block could move, in this case horizontally. So in one direction we're going to have the tension. And in the other direction we're going to have friction. Now if I say the tension is forward, or really in the positive direction, that means the tension is going to be positive, but the friction is going to be in the negative direction, leaving us with the sum of all forces acting on the block in the direction of motion. And we're going to set that equal to the mass of the block times the acceleration of the block, which is 0. And we can do the same thing with the block down here, except there's a trick in this that we have to be careful with. If we said the positive direction of the motion of this block was to the right, allowing this block to move to the right would be the same as allowing this block to move down. So as strange as it may seem, we're actually going to say down is the positive direction for this hanging block. So looking at the net force, we're going to have the weight of the hanging block. I'm going to call that FGH. And then the opposite direction, we're going to have the tension. So that's going to be negative because it is upward or in the negative direction. That also is going to equal the mass of the block times 0. Now you'll notice there's a tension term in each of these equations. So if we rearrange one of the equations for tension and then substitute that in, we get this equation, which is really just telling us that the weight of this hanging block is equal to the friction force between the block and the table. And I'll call this friction on the block, just so we don't get confused about where that friction's coming from. Now if you back up a ways to our definition for friction, friction is given by mu times Fn, where Fn is the normal force. In this case, that is the force by the table on the block. Now since this block isn't accelerating vertically, that means the normal force upward needs to equal the force by gravity or the weight of the block downward. So we can actually say the friction force is equal to mu times the weight of the block. That's going to be its mass times g. Now plugging in our numbers into this equation, we've got a static friction of 0.5. There's a mass of the block that is 2 kilograms, and g, assuming this is on Earth, is 9.8. Which means the friction force is 9.8 newtons. So backing up here to our equation that related the friction force to the weight of the block, we know the weight of the block is going to equal 9.8 newtons. Now since weight is given by mass times acceleration due to gravity, that means the hanging mass is 1 kilogram. So ultimately what this means is if we have any mass here that is less than 1 kilogram, when this block is released from rest, it's not going to go anywhere. But if we were to put more than 1 kilogram right here, when we release this block from rest, it's going to slide and accelerate along that table. Now stick around, and in the next video we'll take a look at the acceleration of this block if we were to put more than 1 kilogram on this hanging mass. I hope to see you then, but on that note, that's all for now.